this. This is a thing that I think is smart to do. So instead of you having to freak out about stuff, there's the link. I think that's
Me?
easier.
You talking to me?
Yeah, I sent you the link.
In where? My
Freak
email?
out about stuff, there's the link. Okay. I sent it to you in Meet. So that
okay.
you have the direct live link, so you don't need to be scurrying around trying to find stuff.
Oh, wait. Wrong class.
Like in the chat for the Meet that we're in.
Okay.
Yeah. I don't know if that's easier or not.
Okay. Got it.
Do a sound check real quick. I don't know if that's easier or not.
Just loading. Okay. Got it.
Yep, I can hear you.
Let me mute myself.
Yep. So we'll just wait a second or two and then we'll be good to go. Yep. Yep, it says I'm live. There it is. Can you try talking real quick?
It's not letting me mute. Hold on one second. Okay, got it.
All right, we're
I'm muted now. Okay, got it.
all right, neat. So we're good. We got it going. It is live and working. Function.
Okay.
I guess I'll keep the window open just in case there's somebody in chat.
All right.
The real question is, where in the world is Mr. Parks? We'll wait like one more minute, and then if nobody shows up, we'll just have to get started. All right, well, I guess we should just get going.
Absolutely. Let's
Cool.
do it.
Yep, here we go. 3, 2, 1. Well, hello there, Earth Science students. How are we
Happy
doing?
Monday.
Happy Monday indeed. Most of you are probably, again, watching this not live, but that is totally fine. Hope everyone's doing totally well under the circumstances. Anyway, we left off last week talking about continental drift. We had the continents in their positions currently, but they had some conflicting information about fossils. There was mountain ranges, coal deposits, their shapes. They had all sorts of things that hinted to perhaps one day long ago they were in a totally different position than they are today. And so we are following that up this week, getting into the mechanics of, well, why? So this guy right here, Alfred Wegener, was the guy who, again, he was a climate researcher and found fossils to be interesting, started piecing together both of those things into a big idea that continents drift, hence continental drift. and he never figured out exactly why it was happening. He saw that fossils had matched up between continents. He saw all these different little signs, but he couldn't ever explain how it was happening. And so he died, and he never really found the mechanism. And it wasn't until like the 60s, 1960s, that we finally really figured out what the mechanism was. And that's what we're going to be looking at today. Well, why do the plates and the continents shift? What is causing these huge land masses to be in different positions than they just, are in? So, first we have to talk about Earth itself, right? Getting back into the different layers that we talked about earlier in the year. So, tectonics, which is what we're talking about now, focuses on the movement of the crust, which is also called the lithosphere, and the asthenosphere, hard word to say, and that is also referred to as the plastic mantle. Plastic as in like it's kind of like plastic. It can be bent. It's not rigid. It's not hard. So we've got the lithosphere, again, is the outer solid shell of Earth that extends to about 100 kilometers deep. That's about 60 miles. And then the asthenosphere, the partially melted portion of the mantle that is under the lithosphere. Again, partially melted doesn't mean that it's fully melted. It means that it's malleable, bendable. So that's why they call it the plastic mantle. And so in that picture right there, you can actually see the crust in the lithosphere is the blue, and the asthenosphere is right beneath that. It's green. So if you were to look in your ES over T on page 10, this is a graph and diagram of the different layers that we had used previously, again, earlier in the year, bringing it back up. And to zoom in on that top part, we're not looking at the temperature or the pressure so much, but we're looking at the different layers. So if you zoom in on that, it shows that plastic mantle in like the gray here, and the lithosphere, which is that tiny bit at the top. So the actual plates, the things that we're talking about that are shifting, are just that black line that's across the top. It's not very thick. It's not like there is this really, really thick thing that's moving around it. Relative to Earth, it's pretty thin. And then the asthenosphere, that kind of ooey gooey, malleable, molten rock, or not quite molten, but semi-melted, is underneath that, and it makes that layer underneath that is going to be moving these things.
Right, that's what I was just going to say. That's what helps it to move. The fact that it is melted, that's what allows the plates to move around.
So we've got this hard, rigid stuff on the top, and we've got this more malleable, ooey gooey stuff underneath. So with that stuff underneath able to move around, it's going to shuffle the harder, more rigid, solid stuff on top around. And that's what's going to cause the plates to be able to move. But again, that doesn't tell us why they're moving exactly. That tells us how they could possibly be moving, but what's the thing that's really driving the asthenosphere to move itself? Well, it has to do partially with density. So to refresh our mind on density, density is essentially how heavy something is, right? Not just in weight, but also within a space. So you could have something like a marshmallow, or you could have a steel marble, and the density will be different between those because there is more matter in a smaller space for the marble, and you know as well as I do, the marshmallow is really, really light feeling. So density between different things can be different, and that's going to lead to what we're going to get into later. Before we get into that, we have to talk about one thing, which is continental crust and oceanic crust. There is the rock that makes up the continents that is actually going to be less dense than the rock that makes up the ocean floor. And you can see here that we've got them at 2.7 grams per cubic centimeter and 3.0 grams per cubic centimeter. So these on the bottom are the two different ones. Continental, which is primarily the rock granite, which you may have heard of from like countertops and other things like that. And then the oceanic is going to be basalt, which again is that heavier, and it's usually darker colored. Yep, that heavier rock. So if you were to look at page 10, you can see that the density is actually shown for those two things, and this is actually going to play a huge role in the movement, as you'll see in a moment. But remember, continental crust is 2.7, oceanic is 3.0. So in terms of which one is heavier per area, the oceanic is going to, well, sink. And that's what we're going to get into next. Floating and sinking. So here, you may have done this in middle school. This is a density column. So you put in a whole bunch of different substances and objects that have different densities, and they will form these layers. Reason being is that each of them isn't going to really mix so much, and they have these different densities that's going to keep them from moving up or down relative to each other. So on the bottom you put the most dense material, and on the top you put the least dense. So on the bottom you have honey, which, as you know, is really thick and is going to be a little heavier than corn syrup, and then maple syrup, and then milk, and then lighter and lighter and lighter, all the way up until you get to this lamp oil. So oil definitely goes to the top. You may have seen it like in water, like if there's oil from your car in a puddle or something, it always goes up to the top. It is less dense. So less dense things float, more dense things sink. This also plays a role in the solid objects. So the ping pong ball has almost nothing to it, right? Very light in your hand. So it's going to float to the top, whereas something metal, like this bolt, is going to sink all the way to the bottom.
It's a good visual of all that stuff.
Yeah, you could do this at home too. If you have any of those different things and you've got, something that's tall and long, you can put things in based on their densities, and you could play around with this yourself. Might be something fun to do while you're home. So why are we talking about dish soap and cherry tomatoes though? Well, this is going to directly go into that continental and oceanic crust. One is less dense, one is more dense. So in terms of like floating and sinking, they are going to have an interaction, and it looks like this. Here on the top, with this mountain range here, we're going to call this continental crust, and this one right here, the one that's beneath it, we'll call oceanic crust. So in their interaction, if they are to bump heads with each other, one is going to sink and one is going to stay up. And so this is going to bring that oceanic plate downwards. It's going to sink underneath it while the other one stays up. This is part of the reason why the plates are going to shift. Because if they do bump into each other or are pushed into each other, they're going to have this interaction. Once you start thinking about the plates as being different densities, and also the material underneath, that molten stuff, being a different density as well, you get a larger picture, which we call convection, which we learned about in the energy unit. We talked about it with the atmosphere, where you had the warm stuff going up, cold stuff coming down. Well, guess what? It's the same thing. Same idea. The movement of heat currents within a heated material because of density differences. So remember that if something is hot, it likes to expand. If it expands, it becomes less dense, so it wants to rise up. Hence, why you get all of that volcanic activity at your mid-ocean ridge. So this occurs in that asthenosphere. Remember, it is malleable, so it can flow, and that is going to be the reason that the plates are going to move. Not only is it the density of the stuff at the top, but it's also the molten or melted, semi-molten, I guess you could say, material underneath that's going to want to rise up and complete these loops, or convection cells. So just to throw another picture over there, or an animation that might help you visualize it. At the top, you've got that thin crust. This would be like the ocean floor you're looking at. And you've got this huge plume of hot material that wants to come up and rotate. Now, this is on an Earth scale, right? We're zoomed out really far. We're looking at a very, very large chunk of Earth in this. This is not a small thing. There aren't many of these loops going on within, a couple miles. This is, thousands of miles long. So you've got this material that's coming up and separating these two plates from each other, where the loops come up, right? That hot material comes up and then spreads out. So that's pushing those plates outward from each other. And also at the edges here, you can just kind of see where, since these are being pushed out, it's going to bump into other plates. This is where the density differences come in and why we were talking about that interaction. So where you've got the continental and the oceanic plate at the lip interacting, you're going to have what we call subduction, where that one plate dives underneath the other. So again, we've got these convection cells. They're going to be moving, pushing that middle part outwards, and then the plates will bump into each other on the sides, where you see these two parts here coming down, and they'll have to either sink, float, or do something else. We're going to get really into what those interactions can be on Wednesday when we start talking about all the different plate boundaries, as we call them. But we're not going to get too deep into that today.
No, just the basic movement today, because there are a few different kinds of plate boundaries, and they all move differently.
Yep. They also have a ton of different features associated, and, well, we'll get into it on Wednesday. All right. So that's really it for what we wanted to talk about today. This is that picture of all the boundaries, and you can see it does get a little hairy with all the different arrows and symbols. But the big idea here was this right here is the process. Convection is the process, the mechanism that was driving the plates to be moving. This circular motion bringing the different plates apart and pushing them also together with other plates. So if you were to take a look back at the mid-ocean ridge, right, you see how that could be making the ocean grow, right? Where the seafloor is pushing out and new material is coming up and forming, pushing the two land masses apart from each other. So folks, you have an assignment in Google Classroom going all over density and how it interacts with different things in the Earth. So go ahead and take a look at that. It's due Wednesday night, I think. Yeah.
Yes.
And it has everything to do with convection and density. Other than that, we have office hours, of course, today and on Wednesday if you need help with that. And we'll be live at 11 o'clock on Wednesday as well.
Yep, just let us know if you need any help. We're here.
You can always email if you can't make it as well. But that's it.
All right.
Short lesson today. All right, folks. Be well, and we'll talk to you soon.